Something at the edge of our solar system is pulling. Not pushing, not drifting, pulling. 6 distant worlds are being tugged off course by a gravitational force that has no name, no confirmed face, and no place on any official map of our solar system. Astronomers have watched this happen for years, and for years, the scientific community buried the idea of what might be causing it. Tonight, we go looking for it. We will travel through the frozen edge of everything we call home, past the last known planets, past the scattered debris fields that mark the end of the familiar. We will visit the 6 silent objects being pulled in the wrong direction. The observatory in Chile, racing to photograph something no human eye has ever seen. And the moment when the math stopped being deniable. If you enjoy this journey, take a second and hit like and subscribe. It keeps us going deeper into the dark. Now, take a breath. We launch. Something was wrong with the math. Wrong in the way that makes a scientist put down their coffee, stare at the screen, and quietly say the numbers do not work. It started with a handful of small, frozen worlds drifting far beyond Neptune. Researchers tracking their orbits noticed something that had no clean explanation. These objects were not moving the way they should. They were being pulled, gently, consistently, unmistakably pulled, all in the same direction, not randomly scattered across the sky the way debris fields should be. Clustered, tilted, aimed. The force doing the pulling had no face, no confirmed source. Nothing in our known solar system was large enough or close enough to do what the data was showing. And that was the problem. For years, astronomers assumed the signal was noise, bad data, confirmation bias. The universe is enormous, and patterns sometimes appear in random arrangements if you look long enough. So they looked longer. They gathered more observations. They ran the models again and again. The pull was still there. 2 researchers at the California Institute of Technology, Konstantin Batygin and Mike Brown, sat with this data for months. Brown was already famous. He was the man who helped strip Pluto of its planetary status, earning the nickname Pluto Killer from the press. So, when Brown said something strange was happening out beyond the edge of the solar system, the community paid attention. Their calculation was simple in concept. If you remove every known gravitational source from the model, and the orbits still cluster the way these 6 objects cluster, then something unknown must exist. Something with mass. Something with a gravitational reach, measured not in millions, but in billions of miles. The odds of the clustering happening by random chance, they calculated, were roughly 1 in 10,000. That is a signal. A real one. But here is where the story gets harder to swallow. The announcement did not trigger a global manhunt. It triggered skepticism. Institutional skepticism. The kind that comes from the enormous cost of being wrong publicly. Other astronomers pushed back. They suggested the clustering could be a selection effect, that we had only looked at certain parts of the sky, and the pattern was a product of where we aimed our telescopes. It was a fair argument. Science works by resisting easy conclusions, but something about the pushback always felt too convenient. The alternative explanation required its own set of unlikely conditions. When researchers ran models with and without a hidden planet to see which one better fit the data, the hidden planet kept winning. Not always, not unanimously, but enough to matter. The signal was real. The debate was real. And somewhere out in the dark, if the math was right, a world the size of several Earths stacked together was tracing a slow, ancient orbit, unseen, unnamed, and waiting. The question was never really whether something was out there. The question was why it had taken this long to start looking, and why, when people did start looking, certain corners of the scientific world seemed strangely reluctant to find it. That reluctance has a history, and it goes back further than most people realize. That history involves reports filed and forgotten, probes that drifted off course, and an infrared satellite that saw something in the dark and could not explain it. Before the hypothesis had a name, the evidence was already accumulating. Pluto's demotion broke something open. On August 24th, 2006, the International Astronomical Union voted. Pluto was stripped of its planetary status and reclassified as a dwarf planet. The headlines were mostly about nostalgia. People mourned the little frozen world they had grown up learning about. Inside the astronomy community, something more significant happened. The demotion was about the region Pluto lived in. The outer solar system, the cold, dark shelf beyond Neptune, was suddenly understood to be far more crowded and complex than anyone had formally admitted. Pluto was one of thousands of objects in a sprawling debris field called the Kuiper Belt. And if there were thousands of objects out there that had barely been catalogued, what else might be missing? This question sounds obvious in hindsight, but science rarely moves on obvious questions. It moves on data. For the first time, the dismantling of Pluto's status gave researchers permission to look at the outer solar system not as a solved chapter, but as a wide-open frontier. Mike Brown, who had done more than almost anyone to push the demotion forward, understood immediately what it meant. He had found several large Kuiper Belt objects in the years before the vote: Eris, Sedna, Quaoar. Each one had revealed new strangeness about the outer edge of the solar system. Each one hinted that the story was far from finished. Sedna was the most unsettling. Found in 2003, it sat at a distance so extreme that no known force in the solar system could have placed it there. Its orbit made no sense under the existing models. Something had either pushed it outward long ago, or was holding it in that strange looping path right now. The official explanation at the time was a passing star, billions of years in the past, that had tugged Sedna into its unusual orbit during the early chaos of solar system formation. A reasonable guess, but unconfirmed. A theory, not a fact. What Pluto's demotion really did was shift the culture. Before it, the outer solar system was textbook material, settled and complete. After it, the outer solar system was a frontier, and frontiers invite the kind of searching that comfortable, settled science rarely does. Brown and Batygin would not publish their Planet 9 hypothesis until 2016. But the seeds were planted the moment Pluto fell. Because if Pluto had fooled everyone into thinking the solar system ended neatly for decades, what else were scientists taking for granted? The answer, it turned out, was almost everything beyond Neptune. The deeper researchers looked into that cold outer shelf, the less it resembled the quiet, empty place the textbooks had described. Something was organizing it. Something with weight, with reach, with patience measured in millennia. An influence so slow and distant that it had been hiding in the data the whole time, waiting for someone to look at the right scale. They just could not see it yet. But what comes next is even stranger, because the clearest sign of that influence was not a single discovery. It was 6 of them, all pointing the same way. 6 worlds, all behaving in ways they should not, all tilted in the same direction, all pointing toward the same invisible gravitational source. The data had been there the whole time. It just needed someone willing to take it seriously. Picture 6 compasses. Scatter them randomly across a table. Now, imagine every single one of them points in exactly the same direction. That is essentially what astronomers found. 6 small worlds in the outer reaches of the solar system, each following its own long looping orbit, each billions of miles from the next. No reason, under standard physics, for them to share any particular orientation. And yet, their orbits were clustered, tilted the same way, aimed at the same invisible point in space, like 6 fingers all pointing at something no one could see. This is the observation at the heart of the Planet 9 hypothesis. It sounds almost too clean to be real. These 6 objects are called trans-Neptunian objects. They live beyond Neptune, in the outer cold of the solar system. They are small, dark, and slow. A single orbit for one of them can take thousands of years. They formed in different parts of the early solar system, were flung outward by gravitational interactions billions of years ago, and ended up drifting in the same general region of deep space, and yet aligned. Betegin and Brown ran the probability calculation multiple times. If these 6 objects were distributed randomly across the sky, the chance of them clustering this tightly was around 1 in 10,000. In astronomy, a 1 in 10,000 coincidence is the kind of thing that gets you laughed out of a conference room. This was a fingerprint. The question was what left it. The most straightforward explanation, the one that fit the data best when plugged into gravitational models, was a planet, a large one, somewhere between 5 and 10 times the mass of Earth, orbiting at extreme distance, looping around in an orbit so vast that it spends most of its time where no telescope had ever deliberately aimed. The gravitational reach of an object that massive at that distance would be exactly the kind of gentle, persistent force needed to herd these 6 small worlds into alignment over billions of years. A slow, patient shaping. The way a current in the ocean organizes debris without anyone steering it. Now, here is the part that keeps researchers awake at night. This is currently a theory. The clustering is real. The orbital data is real. The mathematical prediction of a massive hidden body is published in peer-reviewed journals, but the planet itself has not been directly observed. What has been confirmed is this: the standard model of the outer solar system, without a hidden planet, does a poor job of explaining what we see. Every alternative explanation that has been put forward, observational bias, statistical flukes, the collective influence of smaller known objects, has been tested thoroughly. None of them fully account for all 6 objects at the same time. The alignment is real, the cause is unknown, and the best candidate, the one that makes the equations work cleanest, is something large and dark sitting at the very edge of our solar system, quietly shepherding worlds it has never touched. 6 compasses, 1 invisible magnet. The deeper question is whether that magnet has always been there, or whether something brought it into our solar system from somewhere else entirely. 6 compasses, 1 invisible magnet, and a question that is going to take us further from everything familiar before it brings us any closer to an answer. Hidden does not mean impossible to find. It means we have not looked in the right place with the right tools for long enough. In the case of Planet 9, all 3 of those conditions have been true at the same time. The outer edge of our solar system is not a small neighborhood. From Neptune's orbit outward into the zone where Planet 9 is predicted to exist, the distances are so large that the human mind genuinely cannot picture them without help. Neptune sits roughly 2.8 billion miles from the center of the solar system. Planet 9, if it exists, is estimated to orbit somewhere between 300 and 900 times farther from our star than Earth. Think about it differently. Light travels from Earth to the Moon in roughly 1 second. It takes light about 8 minutes to travel outward from Earth across the inner solar system. To reach Planet 9 at its estimated distance, that same beam of light would take somewhere between 16 and 80 hours. That is how far away hidden means. At that distance, even a planet 10 times the mass of Earth would reflect almost no light back in our direction. It would be extraordinarily dim, colder than most things we can measure, moving so slowly across the sky that distinguishing it from background noise would take months of careful, repeated observation. Telescopes that scan the sky are built to catch fast-moving objects, asteroids, comets, things that shift position quickly enough to be identified in a short window. Planet 9, on its ancient orbit, would move so slowly it would almost look stationary. In a single night's observation, it would appear to be a fixed point, indistinguishable from the billions of other fixed points we call stars. This is a challenge of scale, a profound one. Finding Planet 9 requires knowing which patch of sky to examine, watching that area over weeks and months, and filtering the results for an object that barely moves and barely shines. The predicted location has been narrowed over the years. Researchers have calculated roughly which direction Planet 9's orbit should carry it, based on the gravitational pull the models require. It is thought to be somewhere in a relatively specific arc of the sky, though that arc is still enormous by human standards. Covering it systematically requires telescope time, computing power, and coordinated effort. None of those things are cheap, and funding for a search based on a theoretical object with no direct observation has not always been easy to secure. There is something quietly uncomfortable about that. The math points strongly towards something being there. The alternative explanations have consistently underperformed, and yet the organized, well-funded search for Planet 9 took years to get off the ground. The world is out there, if the models are right. Cold, dark, enormous. Sitting at the edge of the solar system, with the patience of something that has been waiting far longer than we have been looking. The gap between knowing something is probably there and actually finding it is where science does its most difficult, least glamorous work. And the reason no telescope has found it yet has less to do with the object and more to do with the priorities we chose to fund. What is coming next will make the distance feel even more extreme. There is a reason the search has taken this long, and it is not because we lack powerful telescopes. Humanity has pointed instruments at the farthest reaches of the observable universe. We have photographed galaxies from 13 billion light-years away. We have detected ripples in space itself caused by colliding black holes. We have mapped the surface of Pluto from billions of miles out with extraordinary precision. So why has a planet in our own solar system stayed hidden? The answer comes down to something deceptively simple. We have been looking everywhere else. Modern astronomy is organized around the extraordinary. Black holes, gravitational waves, exoplanets orbiting distant stars, the cosmic microwave background left over from the earliest moments of the universe. These are the frontiers that attract funding, prestige, and telescope time. The outer solar system, cold, slow, and apparently quiet, did not feel like a frontier until relatively recently. The telescopes we have built reflect our priorities. Most large observatories scan the sky in surveys designed to catch fast-moving objects or faint signals from distant sources. Planet 9 moves almost imperceptibly slowly. It is dim. It sits in a region of the sky that has not been deliberately targeted with sustained, systematic attention. There is also a physics challenge. At the distance Planet 9 is expected to orbit, the light from our star is roughly 1,000 times fainter than what we experience on Earth. The planet does not generate its own light. It reflects only a tiny fraction of the already thin starlight reaching it at that distance. From Earth, it would appear roughly 100,000 times fainter than the faintest star visible to the naked eye. Detecting something that dim requires long exposure times, sometimes hours per image, across a sky that contains roughly 100 billion observable objects. Researchers have used data from existing sky surveys to narrow the search. The Pan-STARRS telescope in Hawaii and the Dark Energy Survey from Chile have both produced large catalogues of outer solar system objects, and both have been mined for signs of Planet 9. Neither has found it, but both have helped eliminate large regions of sky where it is not. That matters. Ruling out where something is not is real scientific progress, even if it feels like nothing happened. Each eliminated region tightens the predicted location. Each elimination brings the search closer to the patch of sky, where, if the models are right, the planet must be waiting. The Vera Rubin Observatory, now beginning operations in Chile, is the instrument many researchers are pinning their hopes on. It is designed to photograph the entire visible southern sky repeatedly, building up enough image depth over time to catch dim, slow-moving objects that shorter surveys miss. But there is a complication even with that. The predicted location has several possible regions. Some of them lie near the plane of our galaxy, where the density of background stars makes finding a dim, moving object as difficult as searching for a specific grain of sand in a beach photographed from the sky. The search is not stalled. It is systematic, careful, and closing in. But what most people do not realize is that the search was almost never started in the first place, because the people who should have been leading it were, for a very specific reason, looking the other way. Before anyone pointed a telescope at Planet 9, someone sat down and calculated it into existence. That is not unusual in science. It is one of the most powerful things mathematics can do: predict a discovery before the instruments are ready to make it. Neptune itself was found this way in 1846, its position calculated from irregularities in Uranus's orbit before any astronomer had deliberately aimed at it. When the calculations were published, 2 observers independently pointed their telescopes at the predicted spot. Neptune was there. Planet 9 follows that same tradition. But the math behind it is stranger, more contested, and more elegant than most people realize. The core of the calculation comes from orbital mechanics. Every object with mass exerts gravitational influence. The larger the object, the stronger and farther reaching that influence becomes. If you know the mass and approximate distance of a hidden body, you can calculate what its gravitational fingerprint would look like on the objects around it. Battigan and Brown worked in reverse. They started with the fingerprint, the clustered orbits of the 6 trans-Neptunian objects, and worked backward to determine what kind of body could have produced it. The math required a planet between 5 and 10 times Earth's mass. Earth is already large enough to hold a liquid iron core, generate a magnetic field, and sustain an atmosphere and ocean. Something 5 to 10 times more massive would be a world classified as a super-Earth or a mini-Neptune. This type of world is common in other solar systems. It has never been confirmed in our own. The orbit the math predicted is not a simple loop. It is a highly elongated ellipse, tilted at roughly 30 degrees relative to the plane where the other planets orbit. At its closest approach to our star, it might come within a few hundred times Earth's distance. At its farthest, it could be 1,000 times that distance or more. One full orbit takes somewhere between 10,000 and 20,000 years to complete. Let that settle. While humans were developing agriculture, building the first cities, inventing writing, and experiencing all of recorded history combined, Planet 9 has completed less than 1% of a single trip around the solar system. This is confirmed mathematics applied to confirmed observational data. The prediction itself is solid. What remains unconfirmed is whether a real physical object actually matches it. The math has held up to scrutiny better than many expected. Independent teams have rerun the calculations. Some found the clustering less statistically extreme than Battigan and Brown claimed. Others found it more so. The range of mass and orbital distance has been refined over time, but the core prediction, something large, something distant, something on a tilted, elongated orbit, has not been dismantled by any competing team. There is a version of this story where the math is simply wrong, where Planet 9 joins the list of predicted planets that turned out not to exist. Science has to hold that door open. But there is another version, the version where the math is right, where the instruments finally catch up, where some future morning a researcher stares at an image and sees a point of light that moved. That is the version the data keeps pointing toward. And the fact that it has taken this long to mount a proper search has less to do with the math and more to do with what happened when the first people raised their hands and said they thought something was out there. Science has a word for the stage before an idea is accepted. It is not a polite word. It is called fringe. The Planet 9 hypothesis was fringe in no legitimate sense. It came from credentialed researchers at respected institutions, published in peer-reviewed journals, backed by real observational data. but the response it received in parts of the astronomical community carried that energy anyway. The polite, patient dismissal reserved for ideas that challenge comfortable consensus. This matters more than it might seem, because the years of disbelief were not just uncomfortable for the researchers involved. They slowed the search. They reduced funding. They kept the question in contested uncertainty long after the evidence had earned a more serious response. The central critique was observational bias. Critics argued that the trans-Neptunian objects used to identify the clustering were not a representative sample. Astronomers had focused on certain regions of sky, the ones more accessible from major observatories and less obscured by the dense star fields of the Milky Way. If you only look in some places, critics said, your data will naturally cluster in those places. The pattern might be entirely a product of where the telescopes pointed. It was a serious argument. Batygin and Brown took it seriously. They modeled the selection effects carefully. They compared the predicted bias against the observed clustering. Their conclusion? Even accounting for where the telescopes had looked, the clustering was still more extreme than selection effects alone could explain. Their critics said the analysis was insufficient. The argument went back and forth in journals and at conferences for years without resolution. Meanwhile, new trans-Neptunian objects were being discovered. Some came from surveys specifically designed to cover more uniform regions of sky, avoiding the original bias problem. These new objects still showed the clustering. That should have settled things. It did not. There is something in institutional science that resists rapid updating. The cost of being wrong on something this significant is enormous. If a major telescope program is redirected towards searching for a planet that does not exist, that is funding, telescope time, and careers spent on nothing, caution is not irrational. But caution, stretched long enough, becomes inertia. And inertia allowed a decade to pass with the question still officially open, when by any reasonable reading of the accumulated evidence, it deserved sustained, organized, well-funded attention. Several researchers who supported the hypothesis early described the period as professionally uncomfortable. Raising Planet 9 at conferences invited skeptical questions that bordered on dismissive. Grant applications that mentioned it required careful, defensive framing. All of that has shifted significantly in recent years. The skeptics have not disappeared, but the consensus has moved. The question is no longer whether the clustering is real. The question is what is causing it. And the more researchers have tried to explain it away with alternative models, the more the hidden planet explanation has survived every attack thrown at it. Disbelief slowed the search. It could not stop it, because the data kept arriving, and the data kept pointing the same direction, deeper into the dark, toward something that, as it turns out, may have been quietly announcing itself for decades in ways nobody was prepared to interpret. And the first of those signals arrived long before any modern hypothesis existed to make sense of it. It arrived as a faint infrared source in data from a satellite that most astronomers had already stopped thinking about, before Batygin and Brown, before the 6 clustered worlds, before the Planet 9 hypothesis had a name. There was a report. It sat in scientific archives, quietly, largely unread by the generations of astronomers who came after it. In the early 1980s, the infrared astronomical satellite was launched into orbit. It was the first space telescope designed to survey the sky in infrared light, detecting heat rather than visible brightness. In infrared, cold objects that would be nearly invisible to standard telescopes could suddenly be seen for the first time. The satellite scanned the entire sky. It found hundreds of thousands of sources: galaxies, dust clouds, asteroids, distant stars. And in its data, researchers noted something unusual: a dim, cool infrared source that did not match the profile of any known object. It appeared in certain scans. It was large enough and cool enough to possibly be a planet-sized body located much closer to us than any galaxy. The team published their findings. Scientists discussed it briefly, and then the discussion faded. Follow-up observations produced ambiguous results. The source was not clearly redetected in the same location during subsequent observations. Some researchers concluded it was a distant galaxy, misidentified in the initial scan. The story moved on, but the alternative explanations were never fully satisfying. The original team had described the object as potentially as close as 50 billion miles from our star. A galaxy at that position would have been detectable by other means. A dark, cold, planet-sized body would not have been. This is a theory. The source may have been a misidentification. Science produces false positives. It is part of the process. But the timing is worth noting. That infrared data arrived roughly 30 years before the Planet 9 hypothesis gave researchers a framework to revisit it with purpose. During those 30 years, no organized effort was made to re-examine the data with the specific question of a hidden outer planet in mind. When researchers did go back and look after the hypothesis gained traction in 2016, the original data was too limited in resolution to draw firm conclusions. The technology of the 1980s could detect that something unusual was there. It could not say precisely where. That infrared satellite was also not the only early data point suggesting something unusual in the outer solar system. Pioneer 10 and Pioneer 11, spacecraft launched in the early 1970s, both showed small, unexplained deviations in their trajectories as they left the solar system. For years, these were attributed to potential gravitational influence from an unknown body. Those deviations were eventually explained by the pressure of heat radiating from the spacecraft themselves, a real and well-documented phenomenon called thermal recoil. That explanation is confirmed and accepted, but the pattern of early signals being explained away or set aside without exhaustive follow-up is hard to ignore when you look at the full history together. None of this is evidence of a cover-up. Scientists were working with limited tools and competing explanations. That is how science works. What it is evidence of is a recurring pattern. Something at the edge of our solar system has been hinting at its presence for decades. Each hint was individually dismissible. Taken together, across 40 years of data, the picture starts to look less like noise and more like something waiting to be properly seen. When Mike Brown found Sedna in 2003, he almost did not believe the numbers. Sedna sits at a distance that breaks the standard model of how our solar system formed. At its closest approach to our star, it is roughly 76 times farther out than Earth. At its farthest, it swings out to more than 900 times that distance. Its orbit is so extreme, so elongated, so far from anything that should have influenced its formation, that the existing models of solar system evolution had no clean explanation for how it got there. The orbit is real. The distance is measured. The strangeness is not in dispute. That part is confirmed. The leading explanation at the time was a passing star. During the chaotic early period of the solar system, when billions of objects were being flung around by gravitational interactions between the young planets, a nearby star could have passed close enough to pull objects like Sedna into unusual orbits. The solar system formed in a stellar nursery surrounded by other young stars, some of which would have passed through or near our region of space before drifting away. This explanation is reasonable. It is supported by models of early solar system formation. It is a credible theory, but it requires the encounter to have happened billions of years ago, leaving no other clean evidence behind. And it does not explain why Sedna's orbit looks specifically like what you would predict if a massive distant planet were holding it in place right now. Here is the detail that matters most. Sedna never comes anywhere near the Kuiper belt. It never passes through the region where gravitational interactions with Neptune or the other giant planets could have shaped it at any point in its orbit. Whatever influenced Sedna is either ancient and gone, or still out there, still active, still pulling. When the Planet 9 hypothesis arrived in 2016, researchers immediately checked whether a hidden planet could explain Sedna's orbit along with the 6 clustered trans-Neptunian objects. The answer was yes. A planet in the right mass range and orbital configuration could account for both simultaneously. One body solving 2 separate mysteries at once. In science, when a single proposed explanation resolves multiple independent anomalies, that is compelling evidence. Very compelling. A second Sedna-like object was later discovered. Its technical designation is built for databases, not conversations. What matters is that this second object has an orbit almost as extreme as Sedna's. Finding a second impossible orbit in a region where impossible orbits should not exist was something that nobody could dismiss with a shrug. 2 objects with extreme orbits, both behaving in ways consistent with the influence of something large and distant. 6 other objects all tilted in the same direction. An infrared signal from the 80s that was never fully explained. Pioneer probe deviations that were accounted for but still added to the larger picture. None of these are individually definitive. Science requires that honesty, but together they form something that is harder and harder to dismiss with each passing year. And the clearest version of that something, the cleanest and most explicit version, is 6 small worlds, all pointing at the same invisible spot in space. 6 arrows, 1 target. What that target might actually look like, if you could somehow travel there, is something most people have never stopped to picture. Let us slow down and look at the 6 objects directly. The clustering at the heart of the Planet 9 hypothesis is easy to describe in abstract terms. 1 in 10,000 odds, orbital alignment, gravitational shepherding. These phrases communicate the strangeness without quite making it feel real. The objects themselves make it feel real. Each of the 6 has a name. Sedna, which we covered, is the most extreme and most unsettling, the original impossibility. Then there is a second Sedna-like world, discovered in 2012, carrying an orbit almost as strange as the first. Then 4 smaller trans-Neptunian objects, discovered through various sky surveys over the past 2 decades, each one quietly confirming the same directional bias. All 6 have highly elongated orbits. All 6 spend most of their time at extreme distances, swinging briefly closer to the inner solar system before retreating back into the cold. And all 6 have their orbits oriented in the same general direction, their elongated paths aimed at the same invisible point in space. 6 arrows drawn from different hands, all releasing toward the same target. The statistical analysis has been run many times by many independent teams. The consensus on the clustering itself is solid. It is real, it is measurable, and it is not a product of selection effects alone. Where researchers still genuinely disagree is on the cause. The Planet 9 explanation works like this. A massive object on a large, tilted, elongated orbit of its own would interact gravitationally with the inner Kuiper belt over billions of years. Objects whose orbits happen to bring them into certain resonance with the hidden planet would be periodically nudged. Over enough time, millions and billions of years, those nudges would sort the surviving objects. The ones we observe today are the ones that ended up in stable resonance. And stable resonance, in this case, means aligned. Think of it as a cosmic sorting process. Most objects in the outer solar system were scattered or destroyed over billions of years of gravitational interactions. The 6 that remain in these specific extreme aligned orbits are the survivors. Their survival is shaped by whatever they are in resonance with. If the hidden planet does not exist, then these 6 objects survived and aligned for reasons we do not yet understand. That is not impossible, but it is not a satisfying scientific answer. It is a shrug dressed in technical language. What the data actually shows, what is confirmed and not theoretical, is this. 6 objects are doing something that the standard model of the outer solar system, without a hidden planet, does not fully explain. What remains theoretical is what is causing it. The planet is the best answer anyone has produced. Independent gravitational simulations, run without any assumption that a hidden planet exists, keep arriving at the same result. The most stable configuration that reproduces the observed clustering includes a large body at extreme distance. The math did not set out to find Planet 9. It kept finding something that looks like Planet 9, regardless of how you approach the problem. That is the kind of result that keeps researchers awake. And if you could somehow close that distance, travel from Earth to where this world is predicted to sit, what you would find would not resemble any planet in our solar system. What it would look like is something worth imagining carefully. Close your eyes for a moment and try to picture it. You are standing on Planet 9, assuming it has a surface, and a world this size most likely does beneath a thick atmosphere of frozen gases. The ground beneath you is unlike anything in human experience. The temperature is somewhere between -300 and -350 degrees Fahrenheit. Cold enough that most gases we think of as permanent features of our world, nitrogen, oxygen, carbon dioxide, have frozen solid and settled into the rock beneath your feet like a layer of chemical snow. The sky above you is black, the absolute black of a place so far from any star that light has become almost meaningless. Our star, at this distance, would appear as a single brilliant point surrounded by total darkness, brighter than anything else in the sky by far, but still just a point of cold, distant light. It would give almost no warmth. The surface of this world receives roughly 1,000 times less energy from our star than Earth does. Any internal heat the planet retains from its formation billions of years ago has long since radiated away into the void. This world is alone in a way that has no human equivalent. Now picture its size. A world between 5 and 10 times the mass of Earth would be larger than Earth, though not enormously so. Think of something between Earth and Neptune. A dense rocky or icy core wrapped in a thick envelope of hydrogen, helium, and frozen compounds. Astronomers call this kind of world a super-Earth or a mini-Neptune. It is the most common type of planet found orbiting other stars. Our solar system was thought not to have one. That assumption is exactly what is being questioned. A world this size would almost certainly have moons. Gravity of this magnitude over billions of years would collect debris and hold it close. Those moons would be dark, frozen, and airless, but present, orbiting a world in the deepest cold of the outer solar system. Here is something confirmed by science. Worlds at this distance from a star can still generate internal heat through radioactive decay in their cores. That internal warmth is not enough to make a surface habitable, but it raises a more interesting possibility, one we will return to later in this journey. For now, stay with the image of the surface. The ground cracked by billions of years of extreme cold, the sky absolute and starless except for that one distant point of light, no wind, because any atmosphere this world holds is largely frozen against the surface. No sound, because there is nothing to carry it beneath you, moving in the most imperceptible way imaginable. The planet continuing its orbit 10,000 to 20,000 years for a single loop around a star it barely visits. It is stillness at an extreme that has no name, and if it is real, it has been sitting there since before our species existed, carrying its slow orbit through a darkness we are only now beginning to understand. The question of how it got there, though, is the part that changes everything. The answer involves forces and timescales that reshape everything we thought we understood about the origin of our solar system. To understand what an orbit of 10,000 to 20,000 years actually means, you need a comparison that puts it in scale. Earth completes one orbit in 365 days. That is the definition of a year. Mars takes about 1.9 Earth years. Jupiter takes nearly 12, Saturn takes 29. Neptune, the outermost confirmed planet, takes about 165 Earth years to complete a single trip around our star. Planet 9, at its predicted distance, takes somewhere between 10,000 and 20,000 Earth years per orbit. The last time Planet 9 would have been at the same position it occupies right now, humans were in the middle of the last ice age. Glaciers covered much of North America and Europe. Our ancestors were painting caves in southern France. Written language was still thousands of years away. Since then, the rise and fall of every civilization in recorded history, every war, every invention, every scientific revolution, every generation that looked up at the sky and wondered what was out there. And Planet 9, in that entire span, has moved through less than 1% of its total orbit. This is a confirmed mathematical consequence of orbital mechanics. At extreme distances, gravity's pull becomes so weak that the orbital velocity required to maintain a stable path is almost imperceptibly slow. Planet 9 moves through space at perhaps a few hundred miles per hour relative to our star, compared to Earth's roughly 67,000 miles per hour orbital speed. Slow, not stopped, still moving, still looping, carrying its enormous patient circuit through the dark. This orbital period creates one of the practical challenges in finding it. Because Planet 9 moves so slowly, it does not obviously shift position between 1 year's observations and the next. Finding it requires either catching it in 2 observations separated by enough time to detect the movement, or catching it in a single deep image where its dim reflected light stands out from background stars. Neither task is simple. Both are possible with the right instruments pointed in the right direction for long enough. The orbital period also shapes what Planet 9's surface has experienced over cosmic time. A world that spends most of its orbit at maximum distance from our star, in the coldest, darkest region of its path, and only briefly passes through the slightly warmer inner portion, has never known anything resembling seasons in any recognizable sense. Imagine the closest approach as a kind of summer, except the warmth gained at that closest point is so small and brief compared to the millennia of cold that follows, it would register as nothing more than a fractional increase in the faint light reaching the surface. Then, 19,000 years of returning darkness. This is a confirmed implication of the orbital mechanics. What it means for any chemistry or geology on such a world is entirely theoretical, but here is where it gets genuinely strange. Researchers modelling Planet 9's orbit have found that certain portions of the path would place it in a gravitational relationship with the ice giants that is not random. There are orbital resonances between Planet 9 and Neptune that suggest the planet may have been captured into its current configuration through specific gravitational interactions in the deep past. That word matters. Captured. If Planet 9 did not form where it currently orbits, and there are strong reasons to believe it did not, then it came from somewhere else. And what the models keep returning to reshapes everything we think we know about the origin of this solar system. There is a particular kind of courage in publicly reversing a position. In everyday life, changing your mind is considered a virtue. In institutional science, where careers are built on the consistency and credibility of published claims, it takes something more. It takes data so overwhelming that the cost of holding your original position becomes greater than the cost of admitting you were wrong. Several prominent astronomers who were early vocal skeptics of the Planet 9 hypothesis have, in recent years, quietly moved toward a more open position. The sharp dismissals of 2016 have softened considerably in the years since. What changed their minds was not a single discovery, it was accumulation. The first shift came from the expanding catalogue of trans-Neptunian objects. In 2016, only 6 clustered objects were known. By the early 20s, the number had grown considerably. New surveys, some specifically designed to address the selection bias criticism, kept finding objects whose orbits were consistent with the Planet 9 prediction. None of them decisively broke the model. Some refined it. The core signal kept holding. The second shift came from independent modeling. Researchers who had no personal investment in the hypothesis, who approached it purely as a mathematical puzzle, ran their own simulations. Several arrived at similar conclusions. The outer solar system, modeled without a hidden planet, consistently produced a different distribution of objects than what we actually observe. The model with a hidden planet consistently performed better against the data. The third, and perhaps most important shift, came from a reanalysis of the selection bias argument itself. A dedicated survey called the Outer Solar System Origins Survey, run from Chile and designed specifically to avoid the observational biases critics had identified, produced a new catalogue of Kuiper Belt objects. The clustering in this unbiased sample was less extreme than in the original data. Skeptics took a brief moment of satisfaction, but the clustering was still there. Reduced, not eliminated. The question immediately became, if selection bias explains some of the clustering, what explains the rest? No satisfying answer emerged that did not involve something large at extreme distance. One prominent skeptic published a paper acknowledging that while the case was not closed, the hypothesis deserved more serious attention than the community had been giving it. That paper changed the tone of conferences and grant discussions in ways that were hard to quantify but easy to feel if you were working in that field. The researchers who built the hypothesis had spent years in a kind of scientific isolation, certain of the data but uncertain of the reception. As the community began to shift, they refined the model further. The predicted mass narrowed. The predicted orbital region tightened. The hypothesis became more specific, which made it more testable, which made it more credible. That is how this process is supposed to work. And the shift in the community's posture has had a practical effect. Telescope time is being allocated. Survey strategies are being designed around the prediction. The Vera Rubin Observatory, now becoming operational, has Planet 9 as one of its named scientific targets. The years of disbelief produced something useful in the end. They forced the hypothesis to become harder, more precise, more resistant to easy dismissal. What waits at the end of that precision is either a planet or an explanation stranger than a planet. Both outcomes would rewrite the textbooks, and both are coming closer every year. Some of the most important discoveries in science happen when someone is looking for something else entirely. Dark energy surveys are designed to map the large-scale structure of the universe. They point telescopes at the sky and collect light from billions of galaxies, measuring how the universe is expanding, how matter clusters across cosmic scales, and how the mysterious force that accelerates that expansion behaves over time. These are among the deepest and most ambitious scientific projects ever undertaken. They were not designed to find Planet 9. But the data they produce carries a side effect as valuable as the main result. To map billions of galaxies, you first have to photograph the entire sky in extraordinary depth. And a photograph of the entire sky in extraordinary depth, taken repeatedly over years, is also the best possible tool for finding a dim, slow-moving object in the outer solar system. Researchers working on the Dark Energy Survey, a project based at the Cerro Tololo Inter-American Observatory in Chile, realized this early on. They began mining their galaxy data for moving objects, things that shifted position between observations, the signature of solar system bodies rather than distant fixed galaxies. What they found in the outer solar system was a growing collection of trans-Neptunian objects. Some were known, many were new, and the new ones, when their orbits were calculated, kept showing the same pattern. The clustering that Batygin and Brown had described kept appearing in an independent dataset, gathered by an instrument that had no particular interest in finding it. This is important. When a signal appears in data collected for an entirely different purpose by researchers with no stake in the original hypothesis, the likelihood of it being an artifact of methodology drops sharply. The Dark Energy Survey did not look preferentially in the regions of sky where the hypothesis predicted clustered objects would be found. It looked everywhere, and the signal was still there. The survey also produced something more specific. Among its outer solar system, discoveries were several objects with particularly extreme orbits. Distant, elongated, hard to explain without an external gravitational influence acting on them over billions of years. Each new extreme object added another data point to an already growing pile. There is also something slightly uncomfortable buried in this story. The survey was funded primarily for cosmological research. The outer solar system detections were a secondary product. When researchers wanted to dedicate more of the survey's resources specifically to the Planet 9 search, more telescope time, more targeted observations, they faced the familiar friction of competing scientific priorities. The universe is large, and there is only so much telescope time. Arguments about how to allocate it are the normal, difficult business of science. But the result is that one of the most powerful accidental Planet 9 search tools in existence has been used for that purpose only partially, squeezed in between its primary cosmological tasks. What it has managed to find, even in those partial efforts, has consistently pointed in the same direction, and the instrument being built specifically for this kind of search, the one in Chile that astronomers have been waiting years for, is now finally open. What it does next may close this question for good. The question is whether, when that instrument finally produces a clear result, the answer will match what the math has been saying all along. The math, so far, has a remarkable track record. On a mountain in northern Chile, at an altitude of nearly 9,000 feet, something extraordinary is becoming operational. The Vera C Rubin Observatory is not the largest telescope ever built, but it may be the most consequential for this particular search. Its design was driven by a single obsessive goal: photograph the entire visible southern sky, repeatedly, in enough depth to catch things that have never been caught before. The camera at the heart of the observatory is the largest digital camera ever constructed for astronomy. It captures images covering an area of sky roughly 40 times larger than the full moon in a single exposure. It will photograph the entire accessible sky every few nights, building up a dataset over 10 years that has no precedent in the history of astronomy. For finding Planet 9, this matters in a very specific way. Every time the camera photographs a patch of sky and then photographs it again days or weeks later, any object that moved between exposures stands out. Stars do not move relative to each other on human timescales. Galaxies do not move, but a planet, even one moving as slowly as Planet 9, will shift its position against the fixed background of stars over days and weeks of careful observation. The trick is separating a genuine moving object from the noise. A camera this sensitive picks up cosmic ray hits, satellite trails, instrument artifacts, and countless other false signals. Processing the data requires algorithms as sophisticated as the telescope itself. Teams of researchers have spent years building the software that will automatically flag, classify, and prioritize moving objects in the observatory's images. Planet 9, at its predicted brightness, sits right at the edge of what this telescope can detect. That edge of detection situation cuts both ways. Finding it will be hard, requiring multiple observations across many nights before a dim moving point can be confirmed as real. But the Vera Rubin Observatory is essentially the first instrument in history with a genuine realistic chance of making that detection. Previous telescopes were either not deep enough, not wide enough, or not systematic enough in their sky coverage to catch something this dim and slow. The Vera Rubin Observatory removes all three of those limitations simultaneously. The predicted search will take several years of accumulated data. Confirming a single moving object at this extreme distance requires watching it move enough to calculate a reliable orbit. A handful of detections spread across months of observation will ultimately produce a trajectory. And a trajectory, once confirmed, either matches the Planet 9 prediction or it does not. This is confirmed science. The observatory's capabilities are well characterized. The predicted brightness of Planet 9 is well modeled. The expected detection timeline is realistic. What remains unknown is the result. There is a version of this story where the observatory completes its first major sky survey and finds nothing in the predicted region. That outcome would not disprove Planet 9. The planet could be in a part of its orbit currently hidden behind the dense star fields of the Milky Way, where even this telescope struggles. But it would force a significant revision of the orbital predictions, and there is the other version. The one researchers have been building toward for a decade, a point of light, moving slowly, exactly where the math said to look. If Planet 9 is real, the next question everyone will want answered is where it actually came from. And that answer begins not in our solar system, but in the space between stars. Here is something the textbooks have not fully caught up to yet. Planet 9, if it exists, almost certainly did not form where it currently orbits. This is not controversial among researchers who study solar system formation. The outer reaches of the solar system, the cold, sparse region where Planet 9 is predicted to sit, did not contain enough raw material in the early solar system to build a planet of this size. The density of gas, ice, and dust at that distance from a young star is too low. Building a world 5 to 10 times Earth's mass requires far more material than was ever available that far out. So if it is there, it got there somehow. And how it got there is one of the more extraordinary possibilities in modern planetary science. The most widely considered explanation within mainstream research is that Planet 9 formed closer to our star in the region where the giant planets were assembling and was ejected outward through gravitational interactions with Jupiter or the other gas giants during the chaotic early period of solar system formation. This is a confirmed process. We know it happened to other objects. The Kuiper belt itself is populated largely by objects scattered outward by gravitational interactions with the giant planets. The scattered disk, Sedna, the extreme trans-Neptunian objects, are all understood to be surviving remnants of material thrown outward during that early turbulent era. A planet of significant mass could have been thrown outward the same way. If the ejection happened at the right angle and velocity, the planet would settle into a highly elongated orbit at extreme distance, rather than escape the solar system entirely. Exactly the kind of orbit the Planet 9 models predict. This explanation is a credible theory, well supported by models of early solar system formation. There is a second and more dramatic possibility. Some researchers have suggested that Planet 9 may not have formed in this solar system at all. During the early period when our star was still embedded in its stellar nursery, surrounded by hundreds of other young stars in a dense cluster, gravitational interactions between neighboring stars were common. Objects could be exchanged between stellar systems. A planet forming around a neighboring star could, under the right conditions, be captured by our star's gravity during a close encounter. This is theoretically possible. It has been modeled. The probability is real, and it would explain why Planet 9's predicted orbit is so extremely tilted relative to the rest of the solar system. A planet ejected from this solar system would likely retain some memory of the plane in which it formed. A planet captured from another star system would arrive at whatever angle the encounter dictated. Planet 9's predicted orbital tilt, roughly 30 degrees relative to the plane of the other planets, is consistent with a captured origin. If this second possibility is correct, then Planet 9 is a world formed around another star, in another system, torn loose and captured by our star's gravity in the deep past. It has been orbiting here ever since, in the outermost dark, carrying no record of where it came from. That idea should feel enormous, because it means the edge of our solar system may contain a world that is fundamentally alien to everything else here. And if a planet can arrive that way, the next question almost asks itself. Planet 9 is not just a curiosity at the edge of the solar system. If it exists, its gravitational influence reaches inward, slowly, subtly, over timescales that dwarf human civilization, and the question of what that influence means for the rest of the solar system, including Earth, is one that researchers have only recently begun to model in serious detail. The most immediate confirmed implication is the one we have already discussed. Planet 9's gravity in the models shapes the distribution of trans-Neptunian objects. It herds them, it sorts them, it determines which orbits are stable over billions of years and which are not. This is gravitational influence at the outer edge of the solar system, and it is real in the models even if the planet causing it has not been directly confirmed. The more unsettling question is whether that influence reaches further inward than the Kuiper Belt. There is a long-standing hypothesis in planetary science, one that predates the Planet 9 discussion by decades, that a massive body in the distant outer solar system could periodically disrupt the Oort cloud. The Oort cloud is the vast spherical shell of icy objects thought to surround the solar system at distances even greater than where Planet 9 is predicted to orbit. Comets that visit the inner solar system are believed to originate there, dislodged from their distant paths by gravitational nudges. Under normal conditions, the Oort cloud is stable. Objects stay in their distant orbits for billions of years. But a gravitational perturbation from a passing star or from a massive body on an unusual orbit could nudge Oort cloud objects inward, sending a wave of comets toward the inner solar system over millions of years. Some researchers have proposed that periodic mass extinction events in Earth's history may be linked to exactly this kind of cometary shower arriving in pulses. The timing of major extinctions in the fossil record has been analysed for periodicity, and some analyses have found a recurring signal suggesting large impact events may cluster in cycles of roughly 26 to 30 million years. This is a theory. The statistical evidence is real but debated. The causal mechanism is speculative. But if Planet 9's orbit carries it through regions of space where it could periodically enhance the gravitational influence on the Oort cloud, the implications are significant, measured in millions of years, not human lifetimes, but real. There is also a more direct question about orbital stability closer in. The gas giants, Jupiter, Saturn, Uranus, Neptune, are in a delicate gravitational balance that has maintained the solar system's current structure for billions of years. Planet 9, at its predicted distance and mass, does not significantly disturb that balance in current models. Its influence on the inner solar system is extremely weak at this distance. But the models of early solar system formation suggest the balance was different once, when Planet 9 made its journey outward, whether ejected or arriving from outside. It passed through the region where the giant planets orbit. Those interactions helped shape the current configuration of everything inside. In other words, the stability of Earth's orbit, the spacing of the planets, the arrangement that has allowed complex life to develop, may be partly a consequence of Planet 9's ancient journey through the inner solar system. It helped build this place when it left, and it has been watching from the dark ever since. Shepherding, in the context of planetary science, is not a metaphor, it is a mechanism. When a massive body moves through a region of smaller objects, its gravity does something specific and measurable. It clears certain orbital paths while populating others. Objects that drift into orbital resonance with the massive body, meaning their orbital periods are simple mathematical ratios of the body's own period, get herded into stable configurations over time. Objects that fall outside those resonances get scattered or ejected. Jupiter does this to the asteroid belt. The gaps in the asteroid belt, called the Kirkwood gaps, are orbital zones that Jupiter's gravity has cleared over billions of years. Objects that drifted into those zones were pushed out or flung into other parts of the solar system. The gaps are real, measurable, and directly caused by Jupiter's gravitational influence. This is confirmed planetary science. The Kuiper Belt shows a similar structure shaped by Neptune. The populations of Kuiper Belt objects cluster in certain orbital periods that are resonant with Neptune's orbit. Neptune is the confirmed shepherd of the Kuiper Belt's inner regions. But the outer Kuiper Belt, the region beyond about 50 times Earth's distance from our star, shows a different kind of structure. A sharp truncation. The density of objects drops off far more steeply at a certain point than models of solar system formation predict. Something appears to have cleared this region or prevented objects from accumulating there in the first place. One proposed explanation is the very early passage of a neighboring star, which swept material from the outer disk during the solar system's formation. Another is the scattering effects of the giant planets during their period of orbital migration. A third is Planet 9, whose orbit in the models would intersect regions of the Kuiper Belt in ways that could shape the distribution of objects over billions of years. Each explanation has merits. Each has problems. None of them fully accounts for every observed feature of the outer Kuiper Belt on its own. What is confirmed is the structure itself. The outer Kuiper Belt is not smoothly distributed. It has features, gaps, clusters, and sharp population edges that require explanation. The standard model of solar system formation, without any special additions, does not reproduce these features cleanly. Planet 9, in simulations, does reproduce several of them. When researchers run models of the outer solar system over billions of years with a planet of the predicted mass in the predicted orbit, the resulting Kuiper Belt distribution more closely matches what we actually observe. Objects are scattered into extreme orbits. Certain resonances are populated. The truncation at the outer edge becomes more pronounced in ways that match the data better than any competing model. A model that reproduces an observation is not automatically correct, but it adds another thread to a case that already has many threads pointing the same way. The Kuiper Belt is, in a sense, a fossil record. The distribution of objects within it carries the memory of everything that has acted on it over the past 4 billion years. Reading that record is difficult, but the more carefully it is read, the more consistently it points toward a large, distant, unseen influence. Something shaped this region. Something is still shaping it. And the clearest physical candidate, the one that appears most consistently across the most independent lines of evidence, is a world sitting at the edge of everything we know. What is stranger still is that human beings may not be the first to have wondered about it. This is where we have to be careful. The line between genuine historical curiosity and wishful pattern matching is easy to cross when the subject is as compelling as a hidden planet. So let us be precise about what is confirmed, what is suggestive, and what is pure speculation. What is confirmed? Several ancient cultures described a celestial body beyond the known planets that carried significant mythological weight. The Sumerians wrote about a world called Nibiru. The word appears in cuneiform texts and has been interpreted in various ways by scholars. Some read it as a reference to a crossing point in the sky, possibly a planet or a star, rather than a specific astronomical body. Others have proposed it was simply another name for Jupiter in certain orbital configurations. What is not confirmed? Any direct astronomical knowledge of a distant, slow-moving planet in ancient Sumerian texts. The most dramatic interpretations of Nibiru as a 10th planet on a vast orbital period are the work of 20th century writers, not ancient astronomers. What is genuinely interesting, the Dogon people of Mali in West Africa possessed, for centuries before modern contact with Western astronomers, detailed cosmological knowledge that included awareness of Sirius as a binary star system. The nature and source of that knowledge remains debated among anthropologists and historians of science. What is confirmed about broader cultural patterns? Many ancient civilizations developed cosmologies that included hidden or dark celestial bodies, forces that were real but not directly visible. Whether these represent genuine astronomical observations, philosophical frameworks, or metaphorical constructs is a question that has not been fully resolved. The honest answer is that the ancient evidence for awareness of a distant hidden planet is thin, contested, and unreliable as scientific data. But there is something that does not require ancient mystery to be genuinely thought-provoking. The orbital period of Planet 9, 10,000 to 20,000 years, overlaps almost perfectly with the timescale of major human cultural and climatic transitions. The end of the last ice age, the development of agriculture, the rise of the first urban civilizations, all of these occurred within the last 12,000 years. If Planet 9's orbit carries any periodic influence on the Oort cloud or on the frequency of cometary activity in the inner solar system, then these transitions could, in principle, have occurred during or near a period of elevated cometary impact risk. This is highly speculative. The causal chain from Planet 9's orbital position to Earth's surface is long and uncertain. The connection to human cultural transitions is far more speculative still, but it is the kind of speculation that sits at the productive edge of science, the place where questions are formed rather than answered. What is not speculative is this: humans have been watching the sky for as long as we have been human. The idea that something large and dark and slow might be moving through the outer reaches of our cosmic neighborhood is not uniquely modern. It has surfaced repeatedly, in different forms, across cultures that could not have shared their astronomical thinking. The modern evidence shows something cleaner and stranger than any ancient text, because the clearest announcement that something is out there did not come from mythology. It came from a telescope in Chile, in a moment the scientific community spent several years deciding how to interpret. In 2023, a team of researchers re-examined a large catalogue of outer solar system objects and noticed something that had been hiding in the data for years. The details of their analysis are technical. The conclusion was not. When they applied a new statistical framework to the orbital data, one designed to account for all known observational biases simultaneously rather than correcting for them one at a time, the clustering signal did not weaken. It strengthened. The probability of the observed orbital alignment occurring by chance under this more rigorous analysis was lower than prior estimates had suggested. This was a reanalysis of existing data using better tools, not a new discovery, and it arrived at a result that made the alternative explanations harder to sustain. Around the same period, a separate group working with data from the Atacama Cosmology Telescope, another Chilean instrument designed primarily for mapping the cosmic microwave background, flagged an anomalous source in their data. The source appeared in a region of sky consistent with some Planet 9 orbital predictions. It was dim, cold, and appeared to be slow-moving relative to background stars. The researchers were careful. They described it as a candidate. They noted that the signal could be explained by other means: a distant galaxy, an instrument artifact, a statistical fluctuation. They published their findings as a result, requiring follow-up rather than as a discovery. The follow-up observations were inconclusive. The candidate source was not cleanly redetected in subsequent imaging of the same region. It was also not definitively ruled out. It sits now in the uncomfortable category of unresolved anomalies, real enough to be published, uncertain enough to be claimed by neither side. This kind of result is frustrating for everyone involved. The public wants clarity, researchers want certainty, and what the data keeps producing is something in between. Signals strong enough to pursue, ambiguous enough to deny. But here is the thing about that pattern. It is exactly what you would expect if you were searching for an extremely dim object at the very edge of current instrument capabilities. You would get a series of partial signals, uncertain candidates, and inconclusive follow-ups, until accumulated observations from a powerful enough instrument finally produced an image clear enough to settle the question. That pattern is not evidence of failure. It is the fingerprint of a search at the edge of what current technology can do. The Atacama candidate was probably something else, but its appearance in data from an instrument that was not designed to look for it in a region of sky consistent with the orbital models, is the kind of result that keeps research teams organized and funded and pointing telescopes at the dark. Because in the history of astronomy, the moment before a major discovery tends to look exactly like this: a series of hints, a growing pattern, instruments reaching their limits, and then one observation, sharper than the rest, that removes all doubt. That observation has not happened yet. The scientific community knows it has not happened yet, but they also know exactly what it would look like when it does. And some of them are not at all surprised that it keeps almost happening. That near detection, that almost, is a very specific kind of scientific frustration. It means the instruments are nearly powerful enough, almost is closer than it has ever been. Science advances through elimination as much as through discovery. For every hypothesis that survives, dozens of alternatives get tested and discarded. The Planet 9 hypothesis has survived this long because every alternative put forward to explain the same data has, so far, failed to fully account for it. Let us walk through them. The first major alternative was pure observational bias. Critics argued that the clustering of trans-Neptunian objects was an artifact of where astronomers had been looking, not a real feature of the solar system. Surveys specifically designed to minimize selection effects were conducted. The clustering weakened somewhat but persisted. Observational bias alone cannot carry the full weight of the skeptical case. The second alternative was a collective gravitational effect from many small Kuiper belt objects rather than one large planet. The idea was that the combined gravity of thousands of small objects acting in concert could produce the observed clustering without a single large body. Researchers modeled this carefully. The conclusion was that the Kuiper belt would need to be roughly 10 times more massive than current estimates suggest in order to produce the observed effect. Current observations of the Kuiper belt do not support a mass anywhere near that large. This alternative requires a Kuiper belt that looks very different from the one we have measured. The third alternative was an early stellar flyby. A star passing close to the solar system in the distant past could have arranged the orbits of outer solar system objects into the pattern we observe today. This is a real and studied process. But for a single stellar flyby to explain the current clustering without also producing other features we do not see, it requires very specific conditions. Models of this alternative have produced configurations that partially match the data but consistently fail to reproduce all of the observed features at the same time. The fourth alternative was that the clustering is a statistical illusion produced by a small sample size, with only a few dozen relevant outer solar system objects. Maybe the pattern was simply a product of having too few data points. As the catalogue of known objects has grown through new surveys, this argument has become harder to maintain. The signal has not dissolved with more data. It has held its ground. None of these alternatives has been definitively ruled out. Science does not work that way. But here is the honest summary of where things stand. Every alternative explanation tested against the full body of observational evidence has required special conditions, large unknowns, or significant disagreements with other confirmed aspects of the solar system. Planet 9, by contrast, explains the clustering, is consistent with solar system formation models, and makes specific, testable predictions that have not been contradicted by any new data. In science, the hypothesis that explains the most with the fewest additional assumptions tends to be the right one. That principle has a strong track record, and the alternative explanations, taken together, have started to feel less like a scientific rebuttal and more like a progressively shorter list of things that have not yet been tested. Every one of them has been tried. Every one of them has left something unexplained. Something is out there. The only real question left is what exactly we are calling it when we finally see it. At this point in the journey, it is worth being precise. One of the failures of science communication is the blurring of the line between what is known, what is predicted, and what is speculation. In a story as compelling as this one, that blurring is especially tempting and especially harmful. So here is a clear accounting of where the evidence actually stands. What is confirmed? The clustering of trans-Neptunian objects is real. Multiple independent datasets, including surveys designed to minimize observational bias, show a non-random distribution of outer solar system objects. The statistical significance of this clustering has been debated but not dismissed. This is peer-reviewed, replicated observational fact. What is a well-supported theory? A planet between 5 and 10 times Earth's mass on a highly elongated orbit at extreme distance could produce the observed clustering. This prediction emerges from rigorous gravitational modeling and has survived multiple rounds of independent scrutiny. The theory is specific enough to be testable and has not been contradicted by new data. This is a strong scientific hypothesis, not fringe speculation. What is uncertain? The precise mass, orbital period, distance, and current location of Planet 9. The models constrain these parameters, but do not pin them down exactly. The planet could be at the closer end of its predicted orbit, or the farther end. Different modeling approaches produce somewhat different predictions. What is a theory but not well constrained? The origin of Planet 9, whether it formed here and was ejected outward, or was captured from another stellar system. Both scenarios are physically plausible. Both have been modeled. Neither has been ruled out. What is speculation? The connection between Planet 9's orbit and periodic mass extinctions on Earth. The idea that ancient cultures may have had awareness of it. The possibility that it harbors conditions relevant to life. These are intellectually interesting, but rest on chains of inference too long and uncertain to be treated as scientific conclusions. What is unknown? Whether Planet 9 exists at all. The planet has not been directly observed. The clustering is real. The hypothesis is strong. Until an image is obtained and an orbit confirmed, the question remains open. This honesty is not a weakness of the case. It is the appropriate posture of science toward an unconfirmed prediction. Why does this accounting matter? Because the story of Planet 9 is also a story about how knowledge actually builds. It does not arrive in a single dramatic moment of revelation. It accumulates slowly through the unglamorous work of surveys and reanalyses and model comparisons and eliminated alternatives. The current state of the evidence is more compelling than it was 5 years ago. 5 years from now, it will be more compelling still, or the hypothesis will have been decisively tested and found wanting. Either outcome is a scientific victory. Finding the planet would be extraordinary. Ruling it out convincingly would also be extraordinary. It would force a genuinely new explanation for the clustering, and that new explanation might be stranger than any planet. The honest answer to whether Planet 9 exists is this: we do not know. We have strong reasons to think something is there, and we now have the tools to find out. That last part is what is new, and it changes everything about where this story goes next. If the Vera Rubin Observatory captures a point of light moving slowly across the sky, and the orbit matches the prediction, if Planet 9 is confirmed, the immediate scientific consequences would be unlike almost anything in modern astronomy. Start with the textbooks. Every astronomy textbook in the world describes our solar system as having 8 planets. Neptune is the last. Beyond it, the story becomes one of smaller objects, debris fields, and vast empty space. That description would be wrong. Every version of it, in every curriculum, at every level of education, would require revision. That sounds simple. It is not. The confirmation of Planet 9 would require not just adding a 9th entry to a list, but reconsidering the entire framework of how we understand our solar system structure, its formation history, and its place among the solar systems we have observed orbiting other stars. The structure question is immediate. the solar system currently fits a recognizable pattern: 4 rocky inner planets, 4 giant outer planets, and then increasingly sparse and small debris. Planet 9 breaks that pattern. It is large, but not where large things are supposed to be. It is a super-Earth in a solar system that was not thought to have one. That forces a rethinking of the formation models that described our system as typical. The formation history question follows directly. Where did Planet 9 come from? If it formed closer in and was ejected, the ejection event must have left marks elsewhere in the solar system. Researchers would immediately search for those marks in the orbital structure of the gas giants, in the distribution of Kuiper belt objects, in the architecture of the entire outer solar system. The comparison to other solar systems is perhaps the deepest consequence. Super-Earths and mini-Neptunes are the most common type of planet found orbiting other stars. Our solar system was thought to lack them, making us unusual. If Planet 9 is confirmed, we have one. It is just at extreme distance, in an unusual orbit. That changes how we read the statistics of planetary systems across the galaxy. The confirmation would also immediately reopen the question of whether Planet 9 has moons. A planet of this mass, on this orbit, would almost certainly have gravitational companions. Those moons, dark, frozen, remote, would become the next targets of theoretical study, and, eventually, observational searches with the most powerful instruments we can aim in that direction. There is something else that confirmation would do. It would validate a methodology. The prediction of Planet 9 came from mathematical modeling of orbital anomalies. If the prediction proves correct, it demonstrates that this approach, working backward from gravitational fingerprints to hidden bodies, is reliable at scales far beyond where it has been used before. That has implications for every unsolved anomaly in every other planetary system we have observed. If we can find a planet this way in our own solar system, we can look for hidden bodies in other solar systems using the same technique. The discovery would not just describe what is in our solar system, it would provide a tool for understanding what is hidden in everyone else's. That is what one confirmed photograph would unlock, and it would arrive with a second question immediately behind it, one that nobody has a comfortable answer to yet. This question requires the same precision we applied before. Let us earn the speculation rather than leap to it. What is confirmed? Life as we know it requires liquid water, an energy source, and certain chemical building blocks. On Earth, all three come from proximity to a star. We are in the habitable zone, the orbital distance at which liquid water can exist on a planet's surface. Planet 9, at its predicted distance, is nowhere near any traditional definition of a habitable zone. The energy from our star reaching it is so faint that it contributes almost nothing to any surface temperature. A surface on Planet 9 would be among the coldest environments in the solar system, possibly colder than anything we have directly measured. So, the surface is not the right place to look. But here is where it gets genuinely interesting, and it rests on confirmed planetary science rather than wishful thinking. Moons of giant planets and super-Earths can maintain liquid water oceans beneath their ice surfaces through a mechanism called tidal heating. The gravity of the parent planet flexes the moon's interior as the moon orbits, generating heat through friction deep inside the rock and ice. Jupiter's moon Europa, Saturn's moon Enceladus, both are confirmed to have liquid water oceans beneath their frozen surfaces. Both are among the most compelling candidates for life anywhere in the solar system. The energy source, in those cases, is not starlight. It is gravitational mechanics. A super-Earth at extreme distance, if it has moons of significant size, could generate tidal heating in those moons. The amount of heat would depend on the size of the planet, the orbital parameters of the moons, and the internal composition of those moons. Under the right conditions, physically plausible, though not guaranteed, a moon of Planet 9 could maintain liquid water in its interior or beneath a surface ice shell. This is a theory. We do not know if Planet 9 has moons. We do not know their size or orbital configuration. But the principle is confirmed. Tidal heating is real. It operates in our solar system right now, in bodies we have visited with spacecraft. The mechanism that keeps Europa's ocean liquid does not care whether the parent planet is close to a star or far from it. Distance from a star does not mean the absence of energy. It just means the energy comes from a different source. There is a second energy source worth considering. Radioactive decay in the core of a large planet generates heat. That heat can, in principle, warm the interior of a planet or its moons for billions of years, completely independent of how much starlight reaches them. Some researchers have proposed that sufficiently large bodies at extreme distances could maintain internal warmth long after formation. None of this means life exists in the Planet 9 system. The probability is unknown and cannot currently be calculated. But it means the question is worth asking. The same mechanisms that make Europa and Enceladus scientifically compelling could operate, in principle, at any distance from a star, around any body of sufficient mass. If Planet 9 has moons, those moons deserve a place in the catalogue of environments where the question of life is worth raising. That catalogue has grown considerably in recent years, and the places we find worth asking about keep moving further from where we originally thought to look. Here is something that reframes this entire story. Planet 9, if it exists, would not be a cosmic anomaly. It would be a confirmation of something astronomers have already seen many times in other solar systems, around other stars, in data gathered over the past 3 decades of exoplanet discovery. Hidden planets, planets whose presence is inferred from their gravitational effects on other bodies before they are directly observed, are actually the standard story of planetary discovery. Neptune was a hidden planet in 1846. Its existence was calculated from the gravitational anomalies it caused in Uranus's orbit before any telescope was deliberately aimed at it. When the calculations were published, 2 astronomers independently pointed telescopes at the predicted location within months of each other. Neptune was there, exactly where the math said it would be. In exoplanet science, this approach has become standard practice. Astronomers studying planetary systems around distant stars regularly find evidence for planets that have not been directly imaged. They find them through their influence on the orbits of other planets in the system, through the gravitational lensing effects they produce, and through the subtle wobble they induce in their parent star's motion. These unseen planets are catalogued, their properties estimated, their existence treated as near certain pending direct confirmation. The methodology that Batygin and Brown applied to our own solar system is the same methodology applied routinely to solar systems across the galaxy. The only meaningful difference is distance. The planets being found around other stars are sometimes easier to detect because the ratio of the planet's effect to the observational noise is more favourable. In our own system, the measurements need to be extraordinarily precise to detect the subtle signal of a single distant body against the background of everything else. Many exoplanet systems contain super-Earths and mini-Neptunes at various orbital distances. Some have been found in unexpected locations, far from where planet formation models predicted they should be. Planets at extreme distances from their stars, in highly elongated orbits, have been documented in other systems beyond our own. Our solar system is not unique in potentially having a large, distantly orbiting body. Given what we now know about how planetary systems form and evolve, it would actually be somewhat unusual if it did not. The thing that makes Planet 9 feel dramatic is proximity. It is in our solar system. It is something we could, in principle, one day visit. The Voyager probes, launched in 1977, are now beyond the edge of the planetary solar system. A dedicated mission to Planet 9, launched with more advanced propulsion than anything we currently have, would take generations to arrive. But the trajectory could be calculated. The probe could be aimed. The visit could be planned, long before any human now alive would see its arrival. That possibility, the most remote, the most extraordinary, the most audacious in the history of space exploration, depends entirely on one thing first: finding it. And after everything we have covered, the clustering, the math, the failed alternatives, the converging evidence, the observatory in Chile, now scanning the sky, the question of finding it has moved from whether it is possible to when. The when is closer than most people realize. And the answer, when it comes, will land differently for humanity than almost any other scientific discovery in living memory. Because this is a world, a real physical world at the edge of our own neighborhood, a neighbor we never knew we had. The timeline is realistic now, in a way it was not 10 years ago. The Vera Rubin Observatory is operational. Its survey of the southern sky is accumulating. The predicted region for Planet 9 has been narrowed by a decade of additional orbital data. The algorithms for detecting slow-moving dim objects have been refined by teams who have spent years preparing for exactly this moment. The current best estimate from researchers active in the field is that if Planet 9 is within the detectable range of the observatory, and the models suggest it should be, a detection could come within the first several years of full survey operations. Predictions in astronomy have a long history of humbling the people who make them, but this one is grounded in real instrument performance data and realistic orbital estimates. If the detection happens, here is what the sequence looks like. First, a candidate, a dim point in an image that appears to have moved between observations. The movement is tiny, barely detectable above the noise of the data. The research team flags it. They check the archives for prior observations of the same patch of sky, searching backward through years of images for confirmation that the point was there before, moving slowly and consistently. If the archival confirmation holds, the team calculates a preliminary orbit. They check it against the Planet 9 predictions. They do not announce anything yet. The history of astronomy is full of announced discoveries that collapsed under follow-up scrutiny. They wait. More observations. Months of watching the same point move across the sky. The orbit solidifies. The mass becomes estimable. The trajectory becomes reliable enough to project backward and forward through thousands of years. And then, when the team is certain, when the data is airtight and the orbit matches the prediction and the alternative explanations have been considered and dismissed, they publish. The announcement will be unlike almost anything in modern science. It will arrive as a paper in an academic journal, the way these things always do. But within hours, it will be everywhere. The discovery of a ninth planet, a world that has been circling in the dark for billions of years, while humanity built everything we have ever built, is the kind of news that does not stay in a journal. It will be confirmed, then named, then studied, then, eventually, targeted. A spacecraft mission to Planet 9 is engineering. The challenges are enormous. The distance, the travel time, the communication, delays across billions of miles. But they are engineering challenges. The same ingenuity that sent Voyager beyond the solar system and landed rovers on Mars is equal to this problem given enough time and intention. The confirmation of Planet 9 would give humanity a destination. A world at the edge of our solar system that no human being has ever seen directly. A world whose surface has never been described because no one has ever had the data to describe it. Everything we have covered in this journey, the clustering, the math, the failed alternatives, the accidental signals, the frozen surface, the ancient orbit, the possible moons, the question of life, all of it would snap into sharper focus the moment the image exists. A point of light, moving, exactly where the math said to look. That moment has not arrived yet, but it is coming. The instruments are running. The sky is being mapped. The dark at the edge of our solar system is, for the first time in history, being searched with tools capable of finding what is hiding there. Whatever is out there has been waiting a very long time. We are almost there.